Hello guys, I just have a bunch of clips from some of my videos, but we can still learn even though it's gonna get sometimes interrupted, but I will just upload this. This is second episode, so in the first episode here, link below, we mastered single neuron mathematics. As I said, there are so many research scientists in the world, but architecture of LLM is same for 3 years, since rope and mixture of experts. The only improvement was Muon 6 months ago, the Muon optimizer. And so many new papers, and none of them improve the frontier and none of them remain frontier, they just get forgotten a week after. The only good improvement Muon optimizer happened because researchers understood deeply mathematics around and theory around the models. So in this series we will ignore all of the noise and we will deeply understand fundamentals in mathematics, and those are the things that will help us 2x AI progress and help us invent things. I want you to watch this video and to master backpropagation and forward pass of the single neuron, as well as derivatives, because in this second video we are gonna do the same thing but with matrices. So we will now have multiple neurons instead of a single neuron. I'm using this new study feature by ChatGPT and I like it a lot actually. For this video I curated this chat, which is like a slideshow that I edited and changed and improved, so I will teach you this. First of all, let's say you have input x and w set of weights. Can you calculate forward pass w times x? So I did this with pen and paper, and you should too. Some of you might not know how to multiply vectors and matrices, so you should ask ChatGPT to explain this to you, because most of you know, so we don't need to go over that. I will leave the link to this chat below. So this was my result. 1, 2, and it makes sense because this is identity matrix, so it will not change this x. So after we have this y, our predicted y, can you compute loss? So it's gonna be y predicted minus t, which is our target. So we want to change these weights, find which weights when we'll transform this x into this t. So x times weights equals t, and t is our target and y is predicted. So from the last video you know what loss is. So if you don't know, you need to go to last video that I explained. So this is our loss, mean squared error. And it's mean because we are gonna have just one number in the end, even though we have these vectors. And square, I explained why square is better as loss. So can you tell me why we go from here to this one? Why is this equal? Can you derive this from this? Okay, try now and then I'll show you. If we scroll quite a bit further down, so how do we get this? Okay, so we start from this. We have y to be these coordinates and t, and then when we subtract y minus t, we subtract their coordinates. So in our loss, we want to calculate square of this. But when we multiply this with itself, we need to transpose one of them first. So we need to have this transposed times it, because we need to multiply row times column. So that's how we will calculate our loss. So we can multiply these dimensions. Otherwise, it will not be possible to multiply dimensions 1 by 2 times 1 by 2 dimensions. It's not possible. We need to multiply 1, 2 times 2, 1. Inner dimension must be same. That's why when calculating this loss, we are going to transpose this first. And when we transpose and multiply, we get this equation. So we just get this times this, which is same, so it's squared, plus this times this, which is squared, same, so it's squared. To calculate loss, we just put in the numbers and we get 8 in this case. Then backpropagation. So we know from last video that loss changes with respect to w in the following way. We can apply chain rules. So loss with respect to our predicted y and y with respect to w, because we have two of these functions. Because here we calculated y first, so how does y change with respect to w, and then times how does L loss change with respect to y. So now we will take derivative starting from the last function and then multiply with derivative from the this function. pause the video, otherwise I'm showing you result right now. Okay, this is the rule that we need to know. If we have some scalar and we calculate how it changes with respect to a vector, this is the formula. So we will get a vector and we will calculate scalar with respect to the first element. It's going to be first element, and second element will be scalar with respect to the second element. Hello guys, this is a new course, Ultimate AI Research and Engineering course, so I will just document what I'm learning here. If you go here and click this introduction and motivation, first of all, we will be able to join OpenAI, Google, MIT, whatever. I want to do open source, by the way. I don't want to join these companies as of right now. So, and build world-class models. So the goal for this, what we should be able to do eventually, is break the record on the fastest GPT-2 pre-training. So my idea to do this is just to implement DeepSeek's matrix multiplication that we will be learning right now. And then I think we can break this record, which is currently 3 minutes. So we can maybe bring it down. But anyways, in order to get to that point, we will need to understand a bunch of stuff about LLMs and matrix multiplications and everything. And I will be structuring and documenting it to this course, in this GitHub repository. And you can just click here for the beginner part, click here. So I'm just going to put some ultra beginner things for people who don't know any of this. So Python programming, some data manipulation and PyTorch and stuff. And then the advanced part will be just here. So this is the first lesson of the advanced part. We just click here. This is the same thing here that we will be figuring out. And I want your feedback. So I will be trying to structure this in a good way. And you can tell me what to improve, what to fix, if it's too difficult for you, if it's too easy, whatever. Just tell me, give me feedback. So let's begin. High performance GPU matrix multiplication on H100, H200, H800. These are actually worse than these two. So this is the worst, this is a bit better, this is the best. From scratch. Understanding matrix multiplication fundamentals. So if I just run this connect. Okay, we have the shape, we take shape, so I think I will not go in such detail. I am making this a bit more redundant, so for you who know for whom this is easy, you will have no problem, but this is gonna, I think it's very easy, it will be fast for you. So we need to assert matrix dimensions must match for multiplication, so you need to match this one and this one. That's the MatMul. So this course is more advanced course, so I expect you to know why, and later we will create these more beginner courses where I will explain MatMuls and stuff. So that will be in the beginner section. Okay, initialize result matrix. Yeah, that's gonna, the outer dimensions are gonna be, and the type is gonna be same as of A. So I guess A and B will be same type. I think this is just the baseline we are comparing it with. So we are doing matrix multiplication with 4 loops here. For I, for J, we cycle through K, and then just multiply and accumulate. Here we can explain this plus equals a bit more. So it's basically, you know, when we're multiplying row and column element wise. So we add element of the row times element of the column, like this, the first element of both, plus second element multiplied, plus third elements multiplied. I don't know why I wrote here. Okay. So you see, first elements multiplied, plus second elements multiplied, plus third. And you know, I is staying the same and K is changing. So same row, but going through the elements in the row. And here, same column, but going through the elements in the column. After, so in the end, we will just get this number at ij. And then we can just use this function matrix multiply CPU. So I run it, create some random numbers, but this and this need to be same, and use it. And then we can also have it for NumPy, and we can check the difference between our result, and we don't even print NumPy. Yeah, we just see the difference. So the max difference is very small, because this means 0.0000002 or something like that. 7 places behind decimal point. So I also have this like optional understand the matrix multiplication formula. So for those of you who don't understand it, so I guess this can be hidden like this. We will not go over this, but I don't know if I should put this optional before this. I guess I should. Then we have this performance benchmark. This will just measure time of our implementation versus NumPy. So it takes a list of sizes. If I skip down, we see these matrix sizes. And first I will show you that our implementation takes 0.2 seconds and NumPy takes a lot less because it's a lot more optimized. So it's for this size. And for the next size it's even more. It's 2000x slower. Our is a lot slower because it's not optimized. And here it's 3000 times slower than NumPy optimization. Let's see how benchmarking works. So we have these results, we will just store them. So these results will be this array of like size of the matrix, hour time, NumPy time, and speed up. So those objects will be in this results array. So we start by printing, we create random matrices, measure time here for our implementation and for NumPy. And here just to check if the results are correct, which we can visually check here. Max difference is very small, so the results are same. Optional, why our implementation is slow. If we go check here, matrix multiplication 64 times this 64, multiplications 200,000 additions, total operations 500,000. Complexity is m times n times k because we have 3 for loops. So you see here how we implemented these count operations. It's just a number of multiplications. We multiply all of the elements. It's basically 3 for loops. And then there is one less plus than the number of elements along this k. And so the total operations, and that's it. So it has 500,000 operations. This one has 4,033,000,000 operations. And this one 200 million. That's crazy. Even though it all seems like simple code, it's good for you to understand all of this. So let's go onto CUDA. So now I went here and changed runtime type and to T4 GPU. And then I run this so we can check all of the stuff we have with our GPU. I will return to the code. Let me just see here. Number of GPUs 1. So GPU 0, index 0, Tesla T4. Memory 14 gigabytes, multiprocessor 40, and warp size 32. So what does that mean? A warp is a group of 32 threads that executes the same instructions at the same time on a CUDA GPU. Same instruction at the same time on a, so it gets one instruction but different data. So each of these 32 threads gets same instruction but different data. Is the smallest unit of execution on NVIDIA GPUs. Threads within a warp can share data and are executed in lockstep. I guess it means all at once. And then streaming multiprocessor is a hardware unit on the GPU that contains many warps, shared memory, and cores. Many warps, shared memory, and cores. Each streaming multiprocessor schedules and executes warps independently. They are independent from each other. So 40 streaming multiprocessors on T4, and they can run multiple warps concurrently. And so one warp has 32 threads, don't forget about that. So streaming multiprocessor contains warps, warps contain threads. The more multiprocessors and warps used efficiently, the higher the GPU parallelism. Then let's see this. We have this matrix, and we need to transfer that from CPU to GPU. It takes this amount of time. And then computation. Here, this is the Torch MatMul. So we just multiply it with itself. We measure time. And we measure time CPU to GPU here, and then GPU to CPU back. And then this is just showing. So this is what we see. We see transferring from GPU to CPU is a lot longer than computation. So 20 times more transfer overhead than computation time, transfer time than computation time, and even more for big matrix. So computations are very fast, it seems. And look at this. This computation is faster than this computation, which is weird, but it's not so weird because different matrices will cause different types of arrangements and execution in GPU, and some of them will actually be faster, even though there is more, because GPUs have specific hardware that benefits from some arrangements or types of execution. But you see, the transfer time, the memory transfer, is the most demanding part. Okay, so I'll go down and I'll skip this. This is same. So this is just showing how to put this to CUDA. So you see, device is CUDA. Now you got it on GPU, and then we measure time. You need to first wait before measuring for GPU not to have queued tasks, and when measuring, you also need to synchronize, because this would just measure how much it takes to initialize the task on GPU. So you will wait for it to finish the task on GPU and then end time. But anyways, okay, so this is CUDA kernel in C++. So I don't know what I'm gonna do with this. This is C++. I'll skip it for now. I don't know what I'm gonna do with it, but this just writes C++ file. This one. Okay. So we hear this. Here we have this CUDA thread hierarchy, and I'll just show you what we get as a result. So we got matrix size 1024 times 1024 and block size 16. So let's see prints. You will understand better. Matrix size, number of elements. So you see, each thread will have one element in our case. And so block size will be 16 times 16 because we take this block. And then how many blocks we divide this by this, we need this many blocks to make 1024 elements. And so total blocks is just square. And given that each block has 16 threads, then you get this number times this number, you get this number. So thread 00 block 00 is matrix element 00. Thread 01 of block 00 is 10. And then last thread of the last block, thread 1515 of 6363 block, that's the last element in the matrix. Each thread loads 1024 elements from A, so entire row. Each thread loads entire column. So this is the total memory access. Actually, I fixed it. So it loads the entire row from shared memory, because these rows or tiles are in the shared memory, but not at once, not all at once in the thread. Threads read data tile by tile in chunks, not the full read row column at once. So they read tile, calculate, and then read next tile, etc. When matrix dimensions are compile time constant, the compiler can perform aggressive optimizations like full loop unrolling and better register allocation, which is especially important for small or unusually shaped matrices. Full loop unrolling is a compiler optimization technique where the compiler replaces a loop with repeated copies of the loop body, eliminating the need for loop controlled instructions, like incrementing a counter or checking a condition. This reduces overhead and can unlock further low-level optimizations, such as using registers instead of memory, pipelining or instruction-level parallelism, better instruction scheduling, and vectorization. So this is the difference. We have this loop, and we have that loop unrolled here. So this is what DeepGem does when they compile the code. Tensor Memory Accelerator Hopper GPUs have a dedicated hardware unit for moving data between global and shared memory asynchronously. DeepGem uses Tensor Memory Accelerator extensively to load input matrices A and B and their scaling factors, and to store the output matrix D. This allows the main compute warps to stay busy with math instructions, hiding memory latency and maximizing utilization. Let's do some PyTorch lead code style problems and questions. So, Tensor Broadcasting Wizard. Given two tensors of different shapes, implement a function that performs element-wise multiplication using PyTorch's broadcasting rules and returns both the result and the broadcasted shapes. I have no idea what this even means. We got example here actually. So A is torch tensor 1, 2, 3, 4, shape is 2, 2, and B is this tensor with 2 shape, result shape A, shape B, broadcast multiply AB. I didn't even know solution, but here we have the solution. So it's gonna broadcast automatically if we just multiply them. So if we have these two tensors that have different shapes, it will automatically multiply this one and this one and this one and this one. So this is the result. And then it also returns just shapes here, broadcasted shape, resulted shape, and broadcasted what? The broadcasted shapes for both tensors will be the same as the result shape. So that's why we just pass both. Let's go to the next problem. I couldn't solve this one. I didn't even understand what it was asking. Hugging Face just released small LM3, which is the best 3 billion parameter model, and there is training data, code and open weights and everything. So this is fully open source, and building models like this and releasing it fully with everything, that's what I think I want to do. But there is a lot of time until 10 because it's difficult. I don't know how to do it yet. So it supports 6 languages, advanced reasoning and long context. You see it's above Qwen 2.53b and Llama 3.23b, which is actually very strong. So it's a decoder-only transformer using group query attention and NOPE. So it's with a 3:1 ratio. I'm not sure, I think this means like 1/4 is using ROPE, rotary positional embeddings, and the other 3/4 are not using rope of the head. I think so. It looks like they followed the suit of DeepSeek, where they train reasoning on top of the base model as opposed to fine-tuning before reasoning. So they have instruct model optimized for hybrid reasoning, fully open model, open weights, full training details including public data, mixture and training configs. Long context, train on 64,000 tokens and supports up to 128k tokens using yarn. So this is for rope extrapolation. Multilingual, English, French, Spanish, German, Italian, and Portuguese. Why only European? Are they most common on the internet maybe? Or they have very similar tokenizers maybe. 11 trillion pre-training tokens, that's a lot of compute. I wonder how much compute they used. But the model is only 3B, so maybe it's not even that big. But when you compare 3 billion parameters, Chinchilla laws say that for 3 billion parameters you should use 3 times 20, 60 billion tokens. But they train on 11 trillion tokens, which means that these Chinchilla laws are even underestimating the token counts, because it does make sense that just more tokens will make it better. No weight decay in embedding, so I'm not sure what that is exactly. So you see here, it's sharing a single key and value in a group of for a group of queries. So a group of tokens is gonna share a single key and value vectors, and each token will have a separate query, as I understand. I think that's it. They did ablations and on 100 billion tokens, which is a lot, and they found that performance stays the same, while the KV cache on inference is reduced a lot with group query attention. So they also masked tokens from different documents, because as I understand, when feeding the data, it just appends all of the text from different documents. But then for the current document, they just masked other documents before, so it doesn't attend to those documents because they're unrelated probably, and there is nothing to learn from them when attending to them. They removed weight decay for more stable training dynamics. Here they show all of the hyperparameters, which is crazy. So 2.36 million tokens per batch and 4094 sequence length. This is it, training cluster. 48 nodes of 8 times age 100 GPUs for 24 days at the pre-training stage with total of 22,000 GPU hours. This is insane. 24 days, 48 times 8 GPUs. 384 GPUs for 24 days. This is crazy. So probably about $400,000. I don't know this number, I think is wrong. And this Google Cloud, I don't know what this is, but maybe $500,000. That's still crazy. That is so much. I thought like maybe making a video on training this on free Google Colab GPU, but it's not gonna work, I think. They have some parallelism here. So the model was split across 2 GPUs with tensor parallelism, such that one node holds 4 model instances, and then distributed across 384 GPUs with data parallelism. I don't know why data parallelism is 192 here. I guess because one model is split onto 2 GPUs. So pre-training data, they also tested a bunch of them, and so the first phase 0 to 8 trillion tokens, This foundation stage establishes strong general capabilities with our code core dataset mixture. And then second stage is more math and coding while maintaining good web coverage. Web is still 75% while it was 85% before. And decay phase, just 1.1 trillion tokens, which is a lot actually. The final stage further upsamples math and code, and now it's even higher percentage. It's so random that AI models, there is data and they are good at math and code, exactly what they need to improve themselves recursively. That is so random, and I don't understand how this accident happened, that AI models are best at the things math and code that they need to self-improve recursively. So for reasoning, they created some synthetic data with reasoning traces and reasoning stripped version of reasoning data sets. Guys, as I explained in my YouTube post here, I feel like diffusion LLMs will have better planning and reasoning than autoregressive LLMs, as they can edit their previous thoughts and outputs as we do with our plans and planning. And that's what the recent paper called Survey on Latent Reasoning, I think something like that, also shows. And diffusion LLMs can also allow for truly unified video plus text pre-training in the same latent space, instead of gluing together separate video and LLM models like the current LLMs do. So they just have some linear layer connecting them, stitching them together maybe with one linear layer or a few linear layers or something. So I think this paper, large concept models, is the future. So I'm not just jumping the hype train. This is actually what I think the future is, because first of all, it's representing concepts or ideas in a sentence. So whole sentence is a vector embedding as opposed to a single token in today's large language models, autoregressive LLMs. So the advantage here is that there is a lot more possible representations, a lot more possible concepts and ideas. And this works over all of those infinitely many sentences, while there is only 200,000 tokens or whatever the vocabulary size is. And so because of this needs infinite, works over infinite distribution of data, then it's using diffusion models. Because diffusion models are used in this scenario where there is, for example, infinite possible images to generate, as opposed to having just 200,000 possible tokens to pick from. So tokens are discrete and this data is continuous. So this is a diffusion model, and VJEPA by Jan LeCun. So some people have different opinions, but I think this is actually possibly the future, because first of all, it's converting these highly complex videos into latent representations, because you don't actually need all the pixels, all of the information. This grass, like color, is unpredictable and it's unnecessary to try to predict that. Instead, we just need like our latent representation, like this is a dog, maybe white fur, there is grass and stuff between behind and stuff. So, and the other thing, not only do our representations better because they are compressed into abstract space, but it can also be combined into this latent space together with text, with the concepts. So you can map or combine these concepts with these concepts, and then have the model actually learn from both video and text. And but that's it. That's what I feel like. Like the main benefit is we can combine video and text into same latent space and really unify them. Because we are using same model, we can do both in diffusion. So I feel like this is the maybe 5 to 10 year research that's gonna be really cited, really researched on. Even though right now, like all of these companies American, Chinese companies all work at autoregressive LLMs because they have the shortest term improvements and gains, and that's what companies do, like 1 year in, 2 years in, but 10 years after, like it's done in some labs or universities, not in these for-profit companies. And there are good ideas here for creating modules for explicitly reasoning and planning in both concept models and VJEPA and other versions of JEPA. So we can not only learn unified representation space, but also build modules for reasoning and planning. And I think Diffusion is better for reasoning and planning, as I said before, because it can go back and change plans and modify them, etc. So I was looking into this code base, and it's of large concept models, and it's actually pretty massive. There is 100,000 tokens, or maybe 200,000 tokens. So I copied the entire code, 250,000 tokens, into Gemini, and guys, Gemini is really good at explaining code. Some people maybe don't believe it, but it's really good. I think like it's just good. It's too good. First, I asked it, why is there so much code here? There is like so much code. And this is a significant amount of code because it represents a full-fledged research project and its accompanying infrastructure, not just a single isolated machine learning model. So LCM/models defines the actual neural network architecture, which includes base LCM and two-tower diffusion LCM. So this two-tower diffusion LCM is, I think, the best. And also, I think they trained for a week on 8 times 6 H100 GPUs, I think. So maybe $1,000. But I think they did not implement like FPA training, which makes it like 2 times faster, and muon optimizer, which makes it also 2 times faster. So maybe $250. And maybe there are a lot more optimizations that can be made. I wonder. So maybe this can be done in the future by me or somebody else. We'll see if I do this, but these optimizations, yeah. I am here at Builder Pi at 2-tower diffusion LCM, and sequence length is 2048, which is actually pretty huge. So this is number of sentences. And because sentences encode like 10 tokens, or 15 tokens, or maybe 20 tokens, I don't know. So this would actually be like 20,000 to 30,000 token sequence length, which is pretty huge for the small amount of training they did. So I like this. And then this neural network folder has a bunch of different folders. It's surprising how many it has. For example, schedulers. This is denoising schedulers. So this is just scheduling at each denoising step what percentage of tokens will be masked and what percentage will be denoised, I guess. If you want to brush up on your knowledge of diffusion models, I will not explain everything from here from scratch. You can go to my channel and scroll down on videos and see here diffusion LLM. And there are more. You can just see here, I don't know, here, diffusion transformer, diffusion core math, diffusion from scratch. Those 4 videos. You can pick ones or all that you like. For example, they have like whole attention here. I'm wondering why they are not using just like PyTorch attention, or let's ask. I guess they're using some normalizations and some custom stuff and rope. Let's see some ideas for make diffusion LLMs reason better. One main quality is that it can generate in non-autoregressive order. So for example, it can generate return function before it generates the body of the function. So return of the function. So this lets it plan in advance. Maybe it can generate comments everywhere and then return and fill the code, for example. DeepMind just dropped new LLM architecture right here. I'm not gonna read this, it seems complex mixture of recursions, but you can check if you want. For this we need to know why models collapse on synthetic data, because we will be training it on synthetic code generated data. So mistakes, blend, phrasing and biases get amplified because model is learning from its own outputs or other LLM's outputs, not from human annotated data. But I think if we train on a lot bigger model, then this is just distillation. So it's not as bad. The model overfits to synthetic patterns which are less diverse and more repetitive. The feedback loop leads to semantic drift or even total collapse of generation quality. This is called the model collapse feedback loop, and it's a known problem when training generations on their own outputs. Loss of information diversity. Human data is rich, diverse, and unpredictable. Synthetic data has lower entropy and novelty, lacks the long tail of real-world variation. Yeah, there is a lot of variation in real world. Often misses edge cases, rare words, or nuanced reasoning. Also, what if the next tokens were hallucinated in the data? Mistakes are treated as ground truth during training, and model becomes confident in inaccurate or shallow outputs. So to make it useful, it needs to be filtered, diverse, and augmented carefully, mixed with real human written data. Use high quality generation like GPT-4 or human-in-the-loop filtering. You control entropy, domain, and avoid repetitiveness. It's funny how... Never mind. But if I was to train a small diffusion LLM, then we would distill like a large models generations, and the synthetic data would not be so harmful because it's already expected to perform worse. So distillation is not a problem there. But after our diffusion LLM is able to code, it knows the basic like how to code and stuff, then we can use reinforcement learning to make it find solutions and learn to find solutions and how to structure the outputs and planning. Here, for example, it could work like this. We have a plan and code. Now I wonder if it's better to have a plan like this and then code after, or this plan should be like in the comments, or we can also maybe have comments as well here. I'm not sure which one would work best. And diffusion models, the thing with them is they can go back and edit this plan and add things and subtract things. Maybe add comments as well here, because then it will be easier for it to associate like each comment with the line below, and it will be able to associate like which parts of this code are connected to which parts of this plan.